If you shake the tip of a stick in a puddle of water, you'll create waves. In a similar way, if you shake an electrically charged stick in the air, you'll also create waves, electromagnetic waves. Recall from a study of electromagnetism that a change in an electric field induces a magnetic field, and a change in a magnetic field induces an electric field, whereupon these changes in fields regenerate to form an electromagnetic wave. Electromagnetic waves traveling through free space never change speed. Why? The answer involves energy conservation. If life in free space were to slow down, its changing electric field would generate a weaker magnetic field, which in turn would generate a weaker electric field, and so on until the wave dies out. Energy would be lost and none would be transported from one place to another. In free space, there's nothing to accept this energy. Is energy destroyed? That's a no-no, so light cannot travel slower than it does. If light were faster, the changing electric field would generate a stronger magnetic field, which in turn would generate a stronger electric field, and so on, a crescendo of ever-increasing field strength and ever-increasing energy. Again, clearly a conservation of energy no-no. At only one speed do the fields mutually induce each other indefinitely, carrying energy forward without loss or gain. In 1865, the British scientist James Clerk Maxwell, using only the knowledge of electric and magnetic fields that had been gained in laboratory experiments, calculated that these fields should be able to propagate through space at 300,000 kilometers per second. He had calculated, he was surprised to learn, the speed of light. In a vacuum, all electromagnetic waves move at the same speed and differ from one another in their frequency and wavelength. Their classification according to frequency is the electromagnetic spectrum. Note that the lower frequencies are radio waves, then somewhat higher frequencies, microwaves, then infrared waves, and then we get to the tiny part of the spectrum to which our eyes are sensitive, light. And beyond that, ultraviolet, X-rays, and gamma rays. The lowest frequency visible light appears red, the medium green, and the highest frequency appears violet. And these waves are nearly twice the frequency of red light. Here's a yum photo of the color spectrum. We see it extends from low frequency red to violet and beyond. Here we see that the region below red is infrared, then the part that is visible to humans, and beyond our range of sight, the still higher frequencies of ultraviolet, which cause sunburns. The spectrum extends into the X-ray and gamma ray regions. There are no sharp boundaries between the regions, which actually overlap each other. The spectrum is separated into these arbitrary regions for classification only. We call the speed of light in free space c, easy to remember because it's constant. But in transparent materials, light travels at speeds less than c. To understand this, let's first look at a model of electrons about an atomic nucleus. The electrons of atoms have certain natural frequencies of vibration. It's as if they were connected to the atomic nucleus by springs. Atoms have a springiness to them. When light is transmitted through matter, some of the electrons in the matter are forced into vibration. In this way, vibrations in the emitter are transmitted to vibrations in the receiver. This is similar to the way sound is transmitted. When the tuning fork on the right has a natural frequency that matches the frequency of the incoming sound, it is set into vibration. And these vibrations can transfer to other forks not shown here. In a similar but not identical way, light passes through glass and other transparent materials. One of the things that bothered me when I first became interested in physics was how light, when slowing down in a transparent medium, speeds back up when it emerges into the air. If you fire a BB into a slab of balsa wood, it slows inside the wood. but doesn't speed back up when it emerges from the other side. So why should light? Aha, the answer has to do with this mechanical analogy. When you drop one or more balls against the array of balls, the ones to emerge on the other side are different balls. Likewise with light. Light travels in little bundles of energy called photons. The photons that first encounter a piece of glass are not the same photons to emerge on the other side. Here we see three of many atoms. In A, a photon encounters an atom on the edge of the glass. In B, it sets electrons in the atom vibrating. Guess at what frequency? That's right, the same frequency as the incoming photon. So what occurs in the atom's vibrating electron? That's right. In C, it emits a photon that is just like the incoming photon. The process repeats in cascade fashion throughout the glass. So at the far edge, the photon that emerges from the glass is just like the photon that started the process. Wait a minute. Light travels slower in glass than in air? Haven't we learned that light travels at a constant speed, c? Now here's an interesting point. A photon in free space has one speed c, which happens to be 300,000 kilometers per second, which is the speed of the photons in the free space between atoms. So we must distinguish between average speed of light and c. Because of a time delay between absorptions and re-emissions throughout the glass, light travels at an average speed less than c. Even in air, the average speed of light is slightly below the speed we call c. In glass, infrared waves with frequencies lower than those of visible light cause not only electrons, but the entire atoms of molecules to vibrate. This vibration increases the internal energy and the temperature of the structure, which is why infrared waves are often called heat waves. Glass is not transparent to ultraviolet light nor infrared light, but glass is transparent to visible light. I want to leave you with a question. First, notice that I use the sound of tuning forks in my explanation of light transferring energy from one place to another. Some people still confuse sound and light. So before we progress further into light, here's my question. What is the fundamental difference between a sound wave and a light wave? In their natures and in the speeds at which they travel? Until next time, good energy.